Okay, hello. I will be talking about advection problem implemented with discontinuous upwind Glerkin method with non-conforming mesh refinement. You will find example in Advection 3 tutorial. In addition, you can have a quick look how to run the problem. Running a problem involves the partitioning of the mesh and then kickstarting analysis. I will go to the main point, explaining how this is implemented. I will go into the details, but within the reason, in order to make this video reasonable size. So we'll solve the problem as you can see over here. We have a transport problem. We'll be advecting a level set in that case. And while we will be advecting this level set, we'll calculate the error indicator. Since we're using discontinuous Glerkin, we have a jumps on the elements faces, and we will use those jumps as an error indicator. This error indicator will be used to drive mesh adaptivity. Refined mesh will be non-conforming. It will means that it will have hanging nodes. So I will tell a little about the problem setup, upwind discontinuous Glerkin, what is it, non-conforming mesh refinement, error indicator, and age adaptivity, bit refinement levels, user data operators. So we'll start with something which is rather classical. We have advection problem, as you can see over here, which can be derived from Reynolds transport problem. We have here this term like this, where we exploiting the fact that the velocity field is incompressible in our example, just to make it a little bit interesting, in such sense that to describe the velocity field, we'll use the velocity potential. This is a vectorial potential field. And when we will take the curl of this velocity potential, as you can see over here, we'll get the velocity field. And then the curl, if I will write it explicitly, will be discretized such that in H1 field, scalar field, but we'll implicitly assume that is pointing in that direction when we solve 2D problem. Implementation which you see in tutorials is rather generic, which is supposed to work in 2D and 3D case. In 3D case, vector potential will be described in terms of H curve field. So then, but sticking to the simple case, so we have some field phi, which we approximate a scalar field, but when we will multiply it by the prescribed vector in z direction, we have a velocity potential field. Then curl looking as here, there is a standard thing, or we can express the curl of the field in the indices notation using a Levi-Civita symbol, which is readily available in Morpheme in F-tensor library. This is definition of the Levi-Civita tensor. For 2D case is a Levi-Civita. For 2D case has two indices. Okay, so when you take the curl, then when you take the divergence of the curl, automatically you have a divergence-free velocity field. It means that it's incompressible. On top of that, we will, for our example, in order to not further, our example is quite complex. So to keep it simple, we will assume that we have a zero normal velocity field. So it means that velocity field is like contained in the box, is inhomogeneous velocity field, which looks like that. In addition, as an initial condition, we'll have a level set, and then this level set later on is convected, as you can see over here, by our velocity field. So suddenly that starts to move according to the velocity field. So then, but it's like not problem is initialized in the non-symmetric way, like you can see the levels of the level set. And here is a, so then we put it off center by this XC. XC is over here. This is the center, and then that field is, that level set is convected by velocities. Since the velocities are not uniform, so this level set is not transported like kind of the rigid object. That's why it's changing, we're changing a shape and so on and so on. Okay, this is our problem setup. So to deal with that problem, we use the upwind discontinuous Glerkin. Is a rather classical technique for this type of the problems. So we multiply the whole phi in our case. This is the phi is here a level set. And then it's a time-dependent problem. This is coming from the transport equation, and we multiply that by variance of the level set and integrate over the volume. So second term, we can differentiate by parts, as you can see over here. We can differentiate by parts that term when we have integral, and as a result, we get these two equations. Okay. Then what we can do in addition, we can make a trick that we can, when we have this boundary integral, we can split our domain on subdomains, which we call this P, and then so the whole domain is constituted by the sum of subdomains. Those subdomains, we assume they don't overlap. So when you make a common set of two different subdomains, the common set is 0. Has a 0 measure in this sense. They're touching each other on the skeleton. So then those patches match themselves on the skeleton. On top of that, every patch, we assume that he has unique orientation. So then they pointing those patches in the same direction. So then when two patches meet in the edge, the outer normals from two patches pointing in the two opposite directions. Okay, so when we do that, cool thing is that we don't have to assume that those patches are convex. We have a quite big flexibility in choosing the shape of our elements. Okay, so when we have done that, so now we can when we discretize our domain, which our patches, we can express this equation which you have here as follows. Is here that we have a sum over the patches, and then we have those two terms. And then here you can see that involve integration of the skeleton. Skeleton are those red bits. In our formulation, we can exclude the boundary because we as you can seen before, we assume that this bit is 0 on partial omega on the part of the boundary. Okay. This is our setup. And we have already kind of the discretization. When two patches meet, they pointing in the opposite direction. So as a discretization, we can choose many options. And then in this case, a reasonable choice is whether we will use the triangles or quads. It's a reasonable choice to use Legendre polynomials. They have a nice properties in certain in 1D definitely, because you can easily construct that they are orthogonal to each other. Okay, so then, but in short, the field in every patch is approximated by some polynomial of the arbitrary order. In the example which you see, have seen at the very beginning, we're using a fourth polynomial order, but it can be any polynomial order. If you like, you can even extend that tutorial to have HP adaptivity scheme. Okay, so we're using the Legendre polynomials. Look to the Wikipedia. If you want to have to see how we can construct that polynomials. We can construct them very easily in the recursive manner. In case of the quad is very easy because you can use tensorial product. In triangles is not difficult as well. So then what we have, so we will have integration. As you can see, we will have a we will have a sum integration in the volume. Not that, this is not what I want to have. We have a sum integration in the volume over here and some integration on the skeleton. So, but in order to integrate over the skeleton, you have to access the information from the volume elements, because how the discretization is made, you approximate the level set of this convected field, but in L2 approximation, which is set up inside is sitting on the patches, so it's not existing on the skeleton. So what happens? So what you can do, you can iterate over the skeleton, you can move over those skeleton edges, and each time when you move on the skeleton edges, you choose some integration scheme. So you have some integration on the skeleton, whether it's face in 3D or edge in 2D, then you have to project those Gauss points, integration points, on adjacent elements, and then on those adjacent elements, you can evaluate your level set field. That is not necessary case for the velocity field when it will be discretized in terms of the H1 standard H1 field, but in our case we're using vector potential. So again, to evaluate the velocity, we have to take our vector potential field and calculate the curl of it. So to calculate the curl, we'll have to have access to the derivatives, and then we can calculate only in the volume. So always when we integrate on the skeleton, we have to look on the side elements, domain elements, and then we have to evaluate velocity field there. So in principle, you can notice that when you evaluate this field on the left or right hand side, but this is you can agree what is left, what is right, you will getting at two different values because this field is discontinuous. When you have a nice solution, ultimately you will expect something smooth, but when you discretize, stuff is not smooth. So then what we're going to the key, what is so you have a discontinuous Glerkin, because we have this discontinuous approximation, but how we making it up with discontinuous Glerkin. We can recognize that we have, when we have up some skeleton edge, and this skeleton edge, through that skeleton edge is passing the velocity, so wind, which carry our level set. We can say that when the velocity is in this direction, as you can see over here, when the velocity, so this is the on upwind side and this is downwind side. So the information about the state of the system is carried with the wind. It's not moving against the wind, because this is the only way how the information can move. So now, when we evaluate our integral on the skeleton, as you can, so we have this bit. So the integration of the skeleton we can express in this form, where we have a jump of the testing functions, which you can see that this is difference between the value of the testing function on the left and the value of the testing function on the right. Then we have a jump of the term, which is velocity times the normal, and then you have a normal, which is expressed in this form, which is normal v vector field evaluated on the right hand side times the normal of the right hand side minus velocity on the left hand side times the normal. In principle, because since we dealing with the velocities are derivative from the H1 field, those two things are not velocity on the left, on the right, in principle, don't have to be equal to each other. And finally, so now when we multiply, when we are on the skeleton, we have three choices in principle. We can choose the value when you have at some Gauss points, we integrating that, we can choose the vector value of level set on the left. We can choose the value of the level set on the right, or we can add them together and average, or what is the proper way, we can choose this phi on the upside. Okay, on this side, because it's upwind, so because the information is carrying with the wind. So this is how the discretization can look in the principle for our problem. And then on top of that, because it's a semi-discrete problem, it's semi-discrete because I don't tell how to discretize in time, but this is not important in this context. We can use backward Euler or other integration techniques in time. So at the end, we integrating over the skeleton, and then we can understand it that we going patch by patch, or we can have, but more convenient from computational point of view, we moving over this, we can do patch by patch, and then in each patch we integrating over the boundary, or we can do it differently. We can move over a skeleton and we look at the both sides in order to decide which side is upwinding, and then we choose the upwinding side to integrate. This choice, which we choose in Morpheme for analysis, just to say how we, so then whole method has to be completed by the way how you calculate error indicator. So imagine that I have this element over here in the middle, and this element in the middle has edges. And then what we can do when we calculating jump on each edge, and then we add the jump of each edge into the domain element. This is our error indicator. Jump is value of the error indicator. So we have this jump over the skeleton sides, which is over every side of our element. Jump is calculated, as you can see. We add them together, and we have error evaluator. So what we do, so when we evaluate the error for every element, what we do, we have calculate this eta for every element. We choose some threshold, which is epsilon, and then we deciding to split every element which is some fraction of the threshold. So this is the maximal error on the mesh, and this is the threshold. So for example, every element which has has error larger than the half of the maximal error is refined. This technique is we using in this case. There is one important thing, that we will calculate the errors on some refined mesh. So then we will do a time step. We have a refined mesh, so we have some refined mesh in some places on the time step, but then in the next time step, we will have to perform the two operations at once, make mesh finer in the places when error going higher, and then coarsen the mesh in the places where the error is low. So when we calculate the error on the fine mesh, as you can see over here, so what we can do, so then what we can estimate the error on the coarser mesh by doing the operation like that when element is split. So there it has some parent element, and this parent element inherits all the errors of his children in the additive way. So we add the errors of the children to the parent, and so on. And then you can see, so now we have this coarsen mesh, and then we do operation at the end to the very coarse mesh that we add the contribution from every other side. So this is how we do it. Okay. So now, so we have to, as well, when we do this mesh refinement, I have to add about one thing. So we can see example of refined mesh. We have to introduce some topological restrictions. Those topological restrictions are not emerged from the restrictions of the Morpheme data structures, because they allow to handle them. This is the restrictions of the implementation of this particular tutorial. So imagine that we have, this is a case, imagine that we refine once this big element, and then we refine some of it twice. But there is this neighbor element, as you can see over here, which is refined once. So then you see across of skeleton over here, we have a two hanging nodes. That is forbidden case. And then there is a special bit of the code in the algo in the tutorial, which just for when is that case, like you can see, is forced the refinement of this element in order to prevent the case of the hanging nodes. Okay, so then this is the, you can see this is the proper mesh refinement, and below is as well the proper mesh refinement. Okay, next step. Next step is how we deal in Morpheme with this complex system of the mesh refinements. Some parts about that are explained in the core tutorial 1. So look into description. There is a quite extensive description how the bitref levels work in the Morpheme. In this core 1 example, this conforming mesh refinement is applied for linear transport problem, but we're talking about the mixed formulation, and transport is driven by diffusion, not by advection in that example. So what is the key thing? That you can see that every mesh every entity in the Morpheme has some bit refinement level. So when we upload the virgin mesh, not refined mesh, we have we can set the first bit to the all entities. So then we can, for example, decide to split this entity in the middle. So we decide to split entity in the middle. So as a result, we're creating new entities. We're creating new node in the middle of the edge. We're creating new edges because now this long edge is split on two halves, and then new elements are appearing. But look, so then we're creating new entities, and those new entities on new level has a second bit only set. Yeah, so you can see the second bit in all of those entities is set to 1. But still, we keep these background entities, and then which have a first bit set. But this node, for example, or this edge is shared between both mesh refinements. So they exist physically on the same mesh, but they have to distinguish between them, they have a 2-bit sets. So then, even just to show you analogy, what we can do, we can further refine the mesh. For example, we're deciding to make refine this element in the middle. Okay. Yep. We decide to refine that element, and as a consequence of this, okay. As a consequence of this, we creating these blue elements, which you can see, which has a third bit set as a third refinement level. So you can see some entities like that one has all 3-bit sets. From another hand, these entities are on the second and third refinement, so they have first bit set to 0, but 2 others set to 1. Some entities only exist on the third mesh, some entities exist in the 3 meshes. So then this is the mechanism how we can keep the data. We can refine the mesh, but we don't delete entities. We keep everything together, and then we can move between the entities. Some degrees of freedom, for example, on the entities are shared between the different meshes. That is quite flexible because when you have bits and entities, you can perform the operations. So, for example, you can apply the mask in that way. So you can see, for example, when you choose, you say that I want to see all the entities which exist on the last mesh, and then they are only and they only appeared as a refinement. So I set this mask. So, for example, I want to see all the entities which exist only on the second refinement, but all of them. So I put the mask to all. I set all the bits on, and then I see the second refinement level. I can go back to the previous mesh. So using bitref levels, and those are built in the alt Morpheme data structures, you can travel between the different meshes. You can do projections. You can see the skeleton on the different levels. You can see two children and parents, and then you can traverse where using bit operations. You can travel to the mesh in the easy way without really creating or deleting anything. It's just bit operations. Okay, so you can see, for example, in our case, we have to see the mesh as a domain elements and the skeleton elements. In 3D, domains elements are hexes or deaths. tetrahedrons, and faces will be triangles or quad. But in 2D, we have a domain elements are quads or triangles, and skeleton are edges. And every entity has a bit level, and then you can see we can have this mesh, then which last bit is set, then we refine the mesh, and then suddenly appear the edges, which second bit set only, and then we can refine, and then we have some entities which has a 3-bit set. But those elements, you can see over here, those edges getting shorter and shorter where you have refinement. But what is the difficulty over here, as you can imagine? You can see that the skeleton is like on one side is a long edge. Okay, on one side is a long edge, as you can see over here. It's a long edge, and then it has two shorter edges, as you can see over here, and they meet together. This edge over here has a bit level 0, 1, 0, and then it's meeting its two refined children. So this is parent, and this is child. This is child of these parents. Okay. So there are the entities over here in this, because it's the third level of the refinement. They have a third bit set. So by default, you can increase that. By default, a Morpheme can carry 64 bits. So we're showing here over 3 because this is what I can write. But in principle, we assume that the maximal is 64-bit refinements, and then it's starting the bit format. Okay. And this is allow us as well, because when we work with the parallel environment, it's allow us to send the entities between the processors, do a ghosting, because here we can have a situation, for example, that the part of the mesh is in the processor 1 and another in processor 2. And then of course, when you're calculating things on the skeleton, you have on the processor 1, you have to have a look on the volume on processor 2, and some ghosting is necessary. So we have to transfer all those information through the network in that case. And then when we restrict ourselves to 64 bits, we can pack that nicely. If we next level will be 128 bits, and then we will send in like two long integers between them. The processors when we want to set the bitref level. 64 is efficient. So, as I said, we have to integrate over the skeleton, but it's a tricky thing, because when we do this mesh refinement, as I said, so what we have to do in that case, so imagine that we have a situation like you can see, observe over here. For example, between this and this element over here, that we have a refined mesh, and then we have this jump. So when we have, in fact, our current computational mesh is consisting this big element, and then on one side of the skeleton, and on another side, we have those two elements. So in that case, we have to do operation when you visiting the elements on the side from the skeleton. So what we have to do when we have this skeleton edge, for example, as you can see, we can have a skeleton edge. So this skeleton edge is adjacent directly to this element, but in that case, we have to move over here, and then we have this refined element, but then this is not the part of the computational mesh. We have to jump in, so we have to move to the parent of that element, and then we can evaluate the field over there. Okay, so we have a situation like that. We have integration points, those integration points are imprinted on side element over here, but then in that case, when we have integration points, the elements are integration points are imprinted on this chilled element, but this chilled element is not computational element. Then we go into the parent, and then we evaluate the values on the parent. I will talk, so then how you can see it over here. So we have a skeleton, we imprint the degrees of freedom on the left entity and on the right entity, but in any very systematic way. So then we can traverse through the mesh from the children and the parent. There is another way of doing those things. You can do it. This is the implementation which I choose in this example because it seems to me that is easier to implement. So then the implementation, as I said, is going to take the skeleton element, find the adjacent elements, but on this case is this element and this element over here, but this small element on the left is not the computational element. So you're looking into the parent, so you're projecting degrees of Gauss points from the child into the parent, and then you evaluate the fields there. Another option, equally good option, is that when you have a edge, find the parent entity of the edge, and then find the adjacency and evaluate it over. Both are practically has exactly the same implementation. Okay, so then we have this complex mechanism of the projection integration points from skeleton on the domain elements, and then traversing through the parent of the domain elements if that is necessary. Okay, but always this traversing is a one step, of course, because because of this restriction which we have over here, that we don't allow like to refine the mesh twice without the refining a neighbor at once. So when we have refined the element, we can refine it once. If we want to refine it twice, we have to refine it at least once its neighbors. Okay. So one important thing, just to understand the aspects of the implementation of discontinuous Glerkin in our is the concept of the user data operator in the finite element instance in the finite element instance. So then finite elements can have any shape, any type. It can be skeleton or domain. Finite element instance provides the integration rule and the basis functions. But when you implement you don't implement in principle a finite element in Morpheme as a user. You can, but mostly you don't. You implementing user data operators which operates on the element. So user data operators like provide the abstraction that enable you to make a implementation which is element shape independent. So in fact, in theory, if you will implement, if you have somehow can provide the base functions and you implement your PDE, the weak form for PDE, you can have any shape. You can have even a shaped polyhedron, and your implementation will not change. So what you will notice that very often in tutorials, when you will upload the quad mesh, when your code will work. When you upload the triangle mesh, your problem will work. When you mix those two things together, your problem will work. And so from the thanks to this user data operator, you can have in the same mesh, you can have mixed mixed shapes, and then Alice work when you can deal, when you can construct the quadrature rule and base functions. Having that in mind, now when you have a finite element, for example, is a quad, it has a Gauss points. So then on that element, what you do, you pushing your operators to it, which perform the series of operations. For example, they modify the shape functions, they pulling them to the current configuration. You calculating fields, you integrating your differential operators. So every operator do something. For example, operator can visit a parent element. So for example, when you have a skeleton, it has operator which visiting side elements. So for example, when you have a skeleton element, you have a series of operators. One of first operator is in fact the visiting face element and evaluating a fields on that element. But itself, the side element can execute its own operators, which ultimately leads to the evaluation of the field. But other operations can be performed. So what is the side element? From a generic point of the data structures are not important. What face on side element has to have the special procedure of the projecting of the Gauss points from edge, in that case, into the face. Similar operation of them can be done when you need to traverse through the parents, children, parents. So for example, you define your integration scheme on the child, you perform series of operators on that element, and let's say first operator visiting, before you will do other calculations, visiting the parent element, and then this parent element has a projected Gauss points from the child, but using its own base functions, which own order, and then it's performing the operators. And then as a result of that, in the following operators, the information process, data process on parent are available on child. That is extremely flexible technique, and then allow you for large creativity and doing many things in the non-standard way. So number of the possibilities is vast. So now we're moving quickly to the description of the code. I just don't want to get you bored at that stage. But in principle, what we're using, if we can, we're using a form integrators. So we have some generic definitions of the finite elements, which can build the base functions and can set up the integration schemes. And those base functions are dimension, those elements are dimension independent in our case. It's not mean that in generic Morpheme code, you can mix the different problems in the different dimensions. But in this case, we restrict ourselves to that we have a domain with a certain dimension. As well, you can choose a priori what scheme you want to use to the assemble system. For example, you want to use the PETC functions to assemble your stiffness matrix and vectors. You can choose the integration schemes. This is a static idea of the static polymorphism, that once you implement the physics and then you want to have, for example, faster because you have the regular mesh, you can use the fast integration schemes on quads, which are exploiting the tensor products construction of the base functions. So you can do those things once you implement the problem. As well, here I try to make it dimension independent. So we remember we approximate the velocity as a vector potential, which can be approximated in 2D as a H1 field space, H1, and then in 3D it has to be H-car field. Okay, so there is some bookkeeping. So for example, what we can do, we can upload the mesh with some pre-refinement that we don't have to make a refinement on every step, but only what we have, you building the system, we integrating a system of equations for the particular adaptive mesh refinement level. So then always we make a bookmarking that mesh on which we perform the integration has entities on which we want to have performed the integration. There are current bit ref entities which are current bit ref level. There is entities on which we performing the skeleton integration, have another bit ref level. So when we want to aggregate the degrees of freedom through the whole hierarchy from 0 to the final child refined. So this is we have this and we mark those entities by flashing this third bit in that case, and then so then we will have to as well make when we do time stepping and then we coarsening and refining the mesh. We have to know where from which mesh we want to have a projection. So this is a projection bit. Okay, so we have those markers. So then we define the data structure, which like collect the methods and then define the data structures on we operate. So then when we visit, so when we have a skeleton and we visit elements on the side, we have to like keep the information about what happens with the fields and the base functions on the side. And then we have a state data structure, which keeps the information about the handles of elements on the side. It keeps the information about the indices of the degrees of freedom on the rows and columns, which keeps the information about the base functions and sense of the function. So the sense, so then always sense is 1 for the entity on the left and sense is right for the entity on the right. Sense is -1 on the left and 1 on the right. So then sense takes two values, -1 and 1, and then takes as which is 1, what is the left. And then this is unique marking. I don't go into the whole idea of the sense. It's borrowed that idea from MOAB database. So in order when the local orientation of the edge on the side element corresponds to the canonic orientation of the edge of the skeleton, then sense is 1. When it's not, is -1. Since the all volume elements has the same orientation, okay? So then all the volumes are positives. So then always we have a case that 1 is positive and 1 is negative. We keep the information as well about the value of the fields in this data structure when we over here when we evaluate visiting our sites. And then there is a series of functions, like some function which calculate the initial potential velocity field, function which calculate the level set, read the mesh, set up the problem, initial problem, push the operators to integrate over the domain, set a function which calculates the error, function which allow us to visit the parents mesh going to the down to the base mesh on which we define the velocity field. And then so you can imagine that your convected level set field is like on this refined mesh, which constantly changing, but the velocity field is defined only on the coarse mesh. So this function is an operator which visiting, going through all the parents until its primal parent is met, and then it's evaluating the value of the velocity field on the Gauss point of the children. So this is function, this is the generic element which visiting generic operator which visiting element which visiting the elements on the sides and then evaluating the fields on the skeleton. This is which integrate for integration of the skeleton, which decide which is the upwinding level set, which is down the wind level set, and it's using it to integrate. One of the important aspects of every Morpheme implementation, and then it's coming from Morpheme tradition, that we develop Morpheme for industrial applications. So we have to be from writing a code, we building testing in it, and then, for example, we can generate some initial solution and velocity field for which we know exactly solution, or the left volume integrals has to cancel with the boundary integrals and skeleton integrals. So we can generate the artificial solution for which we know the answer, and then we testing. And for example, in that case, we testing integration of the skeleton. As well, in principle, when we solve the nonlinear problem, we want to have a consistency between the left and right-hand side. So then we using, Morpheme has a built-in special tool for calculating the tangent, directional derivatives, and those directional derivatives are compared with the hand-calculated tangent matrix. So you can supply the right-hand side function which calculate the right-hand side based on using a finite difference. Directional derivative is calculated for the random fields, and then this directional derivative is checked with the directional derivative which is coming from your tangent matrix. Consistency can be checked in that way. This is the function which calculates the level sets, and this is function which calculates the initial velocity field. This is the operator which calculates a projection after you, the time step was made, and then you decide to refine in coarser mesh, and then you call this function to project. And then you say, so this is this projection bit of, you can see, you can specify the projection bit. So you can see, okay, I have a new refinement, old refinement. This old refinement is projection bit from this old mesh. I want to project the data to the new mesh, coarsening, and so on. These are special functions to generic functions for do mesh refinement, because you can have a variance when you calculating initial solution on the coarse mesh, you calculating jump, then you refine, you calculating initial solution on refined mesh where it's needed, and then you do that procedure. Or you can have another procedure, you have a solution on the finest mesh, or like not uniform refined mesh, and then you want to like you solve the advection problem. So in some places you want to refine the mesh, in some places you want to coarser mesh. So then you don't recalculating the advection problem on every level. You just projection error down the levels, and then you building your refinement levels once again. So these wrappers allow me to do that thing. So then this wrapper is for doing mesh refinement for initial solution, and this wrapper is used to calculating mesh when I do a solving time-dependent problem. You can see this wrapper is pretty simple. It has a function for setting a bits for a current mesh, run calculations, set aggregate bit, which tells which degrees of freedom I want to keep, which elements I want to keep on that level, and then function which is threshold function, which decide which elements to refine, which not. And it's quite simple implementation. I will not go into the details because that will take too much time. So fundamental starting, so when you go into down the file is a mine function, and if mine function creates the MOAB database with creating Morpheme instance, and then Morpheme is level set instance created, and a level set instance has only one public function, which is run problem, and then run problem consists those operations: reading mesh, setting up the problem, if debugging flag is checked, is testing the operators, integration on the side, then calculating initial velocity field, then refining make initial mesh refinement. When its initial mesh refinement is done, we calculating maximal error, which we encounter during that refinement, and then we using this variable of maximal error as for calculate when for threshold function. We set up the problem from the scratch. We setting up, reset everything, and then we start to run solve the advection problem. Here, what we have when we have a read the mesh, we just tell, so we were using so-called simple interface, which do most of the things for us in terms of the creating a fields and the finite elements. It's easy because thanks to that, we just, as you can see, you will see in the second, we just say what fields you want to use and what approximation order, and how the creation of the element structures and building a problem is done for you. But since here we were dealing with mesh refinement, where we prescribe from very beginning a number of refinement levels, we set the problem refinement level before we load the mesh to 0, because this is in essence 0, and then so the simple interface don't try to set it up. It's just skipping a part of the setting refinement levels, because then we will do that later on by hand over here. This bit is important because one of the bottlenecks in when you solve the problem is allocation of the memory. And in this example, we don't use the matrix-free method. We using here MUMs, and MUMs using compressed matrices. So it's good if we know in advance how much memory we need. And then in case, so simple interface has a way how it can evaluate, estimate amount of needed memory. But in case of the integration of the skeleton, when you have normally, when you're dealing with two L2 fields, degrees of freedom on the domain elements, interior elements are not adjacent to each other. So when you have a classical L2 fields, so you have only block diagonal matrix. Because we have a discontinuous Glerkin, so the elements on two sides, degrees of the dots on the two sides are adjacent to each other through the skeleton, because we're using the discontinuous Glerkin in this particular case. So, and then in addition, so we have to set the some AJC when we're dealing with the parent elements. So we say in this particular case that the elements has a degrees of freedom. They are adjacent to the skeleton, and the children are as well adjacent. Here I'm a little bit more than it's needed, but this adjacency to the skeleton through the skeleton is essential. Okay, so set up the problem. So then we adding, as you can see, two fields. One, we add the level set field L in L2 space, and then we adding the vector potential field, which is H1 into D. We choose the base, isword base, and then we this one over here is how many coefficients we have per degrees of freedom, because in this case it's both are scalar. Second is a vector, but we choose the direction into the automatically, and in 3D it will be anyway H-car field, which is a vectorial field. So vector is described vector by one coefficient by base function, because base function carry the vectorial quantities. And that's it from the setup. As you can see, you just say what are your fields and you build the problem. And then automatically all the information about the potential agency of your problems are deduced from this information. That needs more clarification, but I recommend that you will look the doctrine documentation about those particular functions. So when you go to the tutorial, you click at the function, you should have some description. If you are confused, you can always ask on Q&A or on the Morpheme channel. Okay, so then we're writing those operators which we push to the elements for integrating a right-hand side. So here we calculating these volume integrals, nothing special for right-hand side. Here we have a function to calculating tangent matrix. I don't go into that. We have quite several examples when such things, how to write these data operators, are explained in details. So we'll look into those tutorials. Here is what is new. I will tell you when you integrating on the skeleton. So we have operator, you go into the skeleton element. So we are on the skeleton element over here, but the skeleton element, of course, do not carry any degrees of freedom. All the degrees of freedom for level set are sitting on the volumes. Okay, so before we will do any integration, so we don't have any base on the skeleton with the level set because it's L2, and then only what we have, skeleton element carry only Gauss points, integration point. It could be Gauss points. So we have to visit first the elements on the side, collect the information from the side, and then we can integrate on the skeleton. So you visiting elements on the side by executing this side element instance. And this side element instance has a nice function that it's transparent for you. You can, of course, control it, but usually you don't do it. So whatever integration rule you will set on the skeleton, it will be imprinted on the side elements. And then the base functions will be calculated on those imprinted Gauss points on the side, and fields will be evaluated on the side. Okay, and then that implementation is generic. It's working with every base, every space in Morpheme. And then once you collect the information from the side, So then you iterating over the sides, and then you do those things which we described. You can calculate those jumps, and then you can integrate them in order to calculating local skeleton right-hand side vector, and finally assemble them in the volume. Okay. Similar, exactly the same copy is happening when you're calculating the tangent matrix. So you visiting the sides, okay, visiting the sides, and then you have you now looping left, right, columns, and then left rows, left, right columns. So then you cover all the combinations. You can be smart with that, because when it's upwinding case, so only like this part which is associated with upwinding will be non-zero. So you can skip certain things when you don't have a upwinding case. One important thing is just that, so Morpheme has this, so now the question is how you have, so imagine that you are on the refined mesh. So imagine that you refine the mesh several times. As you can see over here, you refine the mesh several times. You are on the child element, this small dot over here, and then you have a Gauss points over there because you integrating over the smallest mesh because you want to integrate well. So now the question is, I have a velocity which is defined on the coarse mesh over here. Okay, so how I can do that? So what I can do, I can, for example, take that, project those Gauss points over here, project it over, and land over on the coarse mesh. Then when I am the coarse mesh, I can evaluate. I now have a base functions in which my field is defined, and then with data at hand, I can project that information back. Okay, I can project that information back and integrate on the fine mesh. So that is exactly this. This is done by this operator which you do. This is, so you define the operator which is run on the coarsest mesh over here, and then it's when you land over this is executed when you land on the parent element. You have to just update your base functions, derivatives of your base functions, because this is vector potential, so you have to calculate the curl, so you have to calculate the gradients. So this is the set, you're pushing a set of operators here, and then you're pushing the operator, as you can see over here, which calculating curl of the vector field. This is the specialization which works for the both 2 and 3 dimensions, and with H curl and H1 field in that case. This is calculating velocities of the coarsest mesh. And then here is a special operator, run parent, which is a nice operator which you don't have to implement by yourself, which traversing is in the standards library, which walking through the levels and the projection Gauss points, building the base functions where is needed, and so on and so on. You can make it efficient as much as you like. Okay, so then to calculate to make an integration, so it's like, as we said, we have this stack of the operators, which you operator 1, operator 2, and which perform the functions. So before we integrate over the domain element, so we have to have you pushing the integration to calculating, like you can see right hand side, here is for left hand side. We update the base functions, we evaluate the level set field, we calculating derivative of level set field, then we get the we pushing the operator. So I discussed that function. We write the operator which calculate then the velocities on the coarse mesh. So this calculating velocity on the coarse mesh, but then it's available on the child. data structure, which you locally, everything is local. So practically every variable which you can see in this implementation is local, but one for a threshold, everything is local. So then, so this velocity now is pushed to this operator which calculates the residual on the right-hand side. I talked about it before, and then it does it, and then it's assembled the information. Here we have this get site element. This is the element which, when you are on the skeleton, you call this function, generic function, which visiting the site. So then, this is definition of this element in principle, and then it's nothing very special in it. It's basically I have internally set two operators over here. That one to reset the site data. This is to fill the site data, and then in principle, what happens? This element works like that. When I have a site element, and then I happen to this short edge, but it happened that this element has a children. So then first it projects the Gauss points. That is done for you by standard, and then it's going to the parent and project it to the parent, and then collect the data from the parent when this is necessary. Okay, so everything is done again by looping over the site, which is called from the skeleton, and then traversing through the series of the parent childs, child parent and child parent, as you can see over here. And then everything is done thanks to this operand parent function, which is, as I said, generic function, which takes the argument. When is a parent, what operator I have to, what element I have to use, and when is a final parent, what operation I have to do. So then, final parent, I have to collect the data, and then if I have not a final parent, I have to traverse deeper and deeper. Okay, because you have to understand that I have a skeleton, I have imprint the Gauss points, I go to the parent, and maybe I will have to go several levels until I will go to the very bottom where I have defined the velocities. And because in principle, in this implementation, which you see, you can have a velocities defined on the different mesh, the refined mesh, than the that definition where you that the mesh where you define the level sets. As I said, quite flexible thing. Here is a very quick implementation to evaluate the error. In essence, I have operator, this op error skeleton, which I execute on the skeleton. You can see over here, it's calling op site skeleton, which like collect the data. And then when I collect the data, I calculate the jump, as you can see over here. And then I calculate error for a skeleton. Once I calculate error of the skeleton, I add it to adjacent elements, as you can see over here. Okay, and then when I calculate the error on the finest mesh, I have another set of the function which traverse the parents and projects the. So, for example, I have a refined mesh with the. I have splitted element on 4 parts. I have error at every part. So then when I project that error to the parent by adding all the contributions from the child elements. So parent inherit the errors from the children, but children don't inherit error from the parent. Okay, so then I have this test site FE. So when I write the operator which calculate the divergence of the field and calculate the divergence on the skeleton. So in the certain situations when velocity field is orthogonal to the gradient of the level set, the tested volume integral should be equal to the tested skeleton integral. So this takes place. So I exploit that thing. So locally, I just define those fields which are orthogonal to each other, because I remember that when this is velocity field, potential velocity field, I taking a curl of that and then get velocities. So when I put the same thing here, what I will get, and those are linear, so those velocities is orthogonal to the gradient of the level set. So those two integrals has to be equal to each other. So I evaluate integration. I do integration on the skeleton, integration of the volume, performing here on those two operations over here, and then I expect the same value. If you don't get the same value, I shout it because I introduced some bug. So it's cool because you can, when you will experiment with the code, test it, automatically your error will come out, and then you can, like, you know when you're doing things wrong. Another, because system is complex, so you have to dissect the errors, yeah, and then this allows you to dissect the error. You do integration on the skeleton, or you do integration on the domain wrong, or you, for example, have inconsistency between the tangent matrix and your right-hand side. And this we coming to the situation. So Morpheme has this special operator tester, which works like that. So then when it has a special functions. I will just maybe delete that thing. So this has a function which generate the random fields, and then for some initial solution, and then you can say, this is my range of the random field for the level set. This is range of my random field for velocities. Notice that you can shift it and you can tweak it. You can make it not symmetric, these random fields. Then you can generate the random field for the velocities as well, just below. And then you can calculate, and then you can make random directional derivative. When you have a dense mesh, it's enough typically to check only one random direction, because of one random direction on many elements, it's covered the practically most of the cases. Of course, you can make that in the loop if you want to have several. If you want to have you have a random direction, but you want to have several random directions in the different configurations. But in principle, that is not necessary for most of the cases. So here I generate the random fields, and then I have this function which calculate one by one separately the tangent matrix for a skeleton and tangent matrix for a domain. So basically what I say, first I run this function. This function takes an argument, the domain element or skeleton element, then domain name of the element to evaluate left-hand side for a skeleton, and then what it does, it calls this function, which you can see over here, which calculating directional derivative. Okay, and then when something is wrong, it will shout, because inside of that function, tangent matrix is calculated from the formulas which you have implemented, direction, and then directional derivative is based on that calculated, and from another hand, directional derivative is calculated from finite difference, and all is checked. So you expect that this to be small. I speeding up. So now we have a function which calculates initial level set. If you don't know how to implement such thing, scalar, one example, this is least squared projection, described that well. we have plenty examples for doing that thing. Similar thing is to calculate the initial level set, but in that case, here we're using L2 field, and here we're using H1 field, but practically implementation is without change. Only what is cool over here, we define the problem as a coupled problem when we have advection and the problem associated with calculating of velocities. Here we have velocities fixed, but in principle, we don't have to. They can be calculated from Navier-Stokes equation, for example. So, but what you can see, we have a generic problem, and then we creating in Morpheme sub-problem where we want to, and we calling it, for example, velocity projection, and then we taking from the whole problem only one field, but we can have two or so on. And then we solving the solution of the sub-problem, we can create the matrix for the sub-problem and so on. And then when we do projection, of course, here we're using standard form integrators. So practically a zero implementation, only a setup. Here we just specify on which bit level we want to run, on what mesh we want to run our problem. And then, of course, with everything, is sometimes you want to debug. So what you do, you have some post-processor when you decided to plot the velocity field velocity gradient. Here is operators which evaluate those things. Look to the other tutorials. It's plenty examples which does the similar things in them on the different level of the difficulty. Finally, we going to the key problem. So we solving advection problem. Again, we have a big problem. We treated advection problem as a sub problem, which we solving only for level set method. So we want to we're creating post-processing element which prints the different information at every step, including the error on the elements. Then we have we set up the monitor, which is executed by time solver from which at every beginning of every step. So here we're creating time solver. This is creating PETSI time solver, and then before we start, we set, so we initialize solution, we initialize the vector over here, create the matrix for the given bit left level. With this function, we're using smart pointers to keep the PETSI objects, so they are automatically destroyed when they go out of the scope. And then the key thing. So then we're using let's say a theta solver or a backward order solver. So every beginning of every step, we do pre-step. We tell the PETSI to become a do a pre-step, as you can see defined over here, where you calculate the error, project the error to the parents down the mesh, then start with the coarse mesh and refine mesh until you meet the threshold criteria. So you refine until criteria is for refinement is met. We cap them in the example over here to 3 refinement levels. It could be more, and then we reset time solver. So that is so what you do, because you have a new mesh. So then what we do, we reset time solver. We set up the time solver again. We project the solution from the course. So from the old mesh to the new mesh, we set the solution. We set up new new matrix, and then we carry on with the calculations. So it's here in this example, calculate error, project error, refine mesh, project after refinement mesh, project the solution from the old to new, and the reset time solver. So here I will put that this is how the mesh refinement is happening. So what we do when we have just to make a solution refinement level look nice, what we do when we decided that we want to refine that element, we take the bridge entities through the nodes, so we find those pink entities, and this is what we say that it will be our refined mesh, just in case, because then we it's like refinement is kind of the explicit, so then we calculating for the current mesh, and then solution, so the fields is moving, so we want to make this additional level. So for example, we can improve the solution. So for example, when it's upwinding, so we will refine, we will add those elements only out upwind side. But here we're like taking the additional entities through the edges and then refine slightly more than threshold tensors. Also, is a bit of the code which try to fix this problem of the situation like that, which is forbidden, that are too big jumps. So then we try, this big code in green instances, it fixed the problem of these too many refinement, too big jumps, too big contrast between refined mesh and then not refined mesh. That's fixing the problem. This is forbidden case, and this is the fixed case. Yeah. So how the refinement look like in principle? When we decide which elements we want to refine, we take the elements from the previous refinement level, subtract from previous refinement level entities which we want to refine. We find the children of those entities, and we add them to the current refinement level with the old entities which we don't want to refine. That's described over here. I will put that PDF with these notes on the next in the documentation. Okay, that's not so. In addition, we have to decide which are skeleton elements, and this is the function which takes the skeleton elements. So when we have, for example, a situation like that, we have then we have refine on this side. So then we say that the skeleton elements are always those finer elements. And then, but in the code, what we're saying, there is no degrees of freedom on those finer entities, but we say this is skeleton bit and this is the skeleton bit. But mesh on which we calculating problem integrating is only this big element and those small elements when we have our contrast. So this setting those bits is only bookkeeping. Of course, this is the we refine that refinement in the recursive way, so you can see then we run the n loops, and each loops we make a mesh finer in the places. Last function practically is this function of the projection of the data from one mesh to the another. This again is nothing particularly difficulty. It's just basically going through the parent and child case. Projection can be done very efficiently because when we have L2 field, so we can do it element by element, but still you can do that with the KSP solver, but with the appropriate preconditioner, which exploits the diagonal block of the structure. And then on top of that, you can make it super efficient by running this projection only on the entities which changing between two time steps. Okay, this is all what I want to say. Thank you.